So I want to tell you about forensic chemistry because it's going to have to do with your lab final. So obviously we're going to try and figure out how some of the things that we've done throughout the year turn out to apply to the actual real world. So the first bit deals with what forensics turns out to be, and it's a big broad field. It's kind of like most things in this class where you could actually study it for quite a long time and never finish. Basically, forensics is solving mysteries. I would call it solving mysteries. It usually will involve some type of test or a whole bunch of tests involving knowns or unknowns. A whole bunch of this stuff utilizes chemistry, and we're just trying to solve a question, solve a puzzle, namely, like, what is this, or what is it made out of, or where did it come from, or does this match someone else? That's all we really do in forensics, and it's a lot of the molecular world. There's some physics involved, but it's pretty much molecular. The reason why I said the techniques is mostly from chemistry would be because there's some biochemistry and some molecular biology involved with some of this stuff too. There's some physics involved. There might be some anatomy and physiology, but it's a lot of chemistry. And obviously this has been made famous through when CSI first came into existence and all the other crime shows that are out and about. So what can you solve with forensic analysis? Well, here's a list. And it's not like you haven't heard of any of these things before, because if you ever pay attention to any lick of the news, that's all forensics. Whenever you have documents and you want to know, well, where did these documents come from? That's forensics. If you wanted to look at, I don't know, well, yeah, I'm drawing a couple of blanks. I had some thoughts and then they immediately disappeared. But whenever you think of a crime scene, whether that crime is digital or physical, we can figure out what's going on using forensics. So toxicology, that's are you poisoned? So what's inside of your blood? If you analyze fingerprints, which is more of an anatomy thing, but it's also a probability thing. Alcohol is actually using spectrophotometry. Soil analysis, that deals with pH and composition, DNA, protein. That's the biology world. But figuring out like accelerants or chemical compositions of things, or what is this chemical, all that turns out to be forensics. So obviously we're doing this for a reason, and that's because this is going to be, like I said, your lab final. So what we need to do is, well, what things do you need to remember? Among the first things that we did this school year was density. I'm aware that you don't remember anything from the start of the school year, but we did play around with density. Density is a physical property of matter, meaning it just is what it is, but you could test for density without ever destroying or manipulating what the substance is. Meaning if you were to test for something that's a chemical property, you end up having to destroy or change whatever the substance is. In order to test like the chemical properties of sodium, you're going to turn sodium into something that's not sodium. But if you wanted to figure out the density of sodium, it will be sodium before and it will be sodium after. The equation is density is mass over volume. So whatever the mass is in grams or kilograms or milligrams, whatever you want it to be, the volume will be in liters, milliliters, whatever you want, as long as you can get the right ratio to match a density that you can look up. Meaning if densities in a table are being given to you in grams per liter and you are measuring grams per milliliter, well, you're going to have to do a little bit of math to convert your measurements into the measurements of what's reported. This is usually a pretty easy way to identify some stuff. For example, my mother-in-law had a necklace and she was claiming that it actually was made out of gold, as in solid gold, and it was slightly malleable. You could slightly bend it, and she brought it over to my house. Oh, it was during the school year, and she was, well, this is gold, and my response was, are you sure? And she's like, yeah, because it feels pretty heavy. So I felt it, and like, yeah, it feels kind of dense, but I wasn't entirely convinced. So for reasons we don't care about, I have a graduated cylinder at my house. I was given it. And I've measured its volume. I have a food scale, so I measured its mass. I calculated out its density, and it wasn't pure gold. The density was far too light, or the density was too small. So it actually wasn't gold. And she was, oh, well, okay, because I could demonstrate it using math. And here's what the density should be, and here's what the density of this thing turns out to be. Therefore, it's not gold. Another thing that we can do is if you have a list of descriptors of an element, you could actually figure it out based upon, does it look like a metal or a non-metal? Does it conduct electricity? How well does it conduct electricity? Is it magnetic? Is it malleable, meaning can you warp its shape? How easy does it react? Like, does it rust easily? Does it react with water? Is it toxic? The toxic one's going to be a little harder for us to test. But if you were given a list of properties of elements, you could actually identify the element just by looking at properties of them. Is it a liquid? Is it solid? Is it a gas at room temperature? What color is it? This is actually not insanely difficult to do. You could also figure out certain elements. It doesn't work with all of them by doing a flame test or looking for colors. So here in the upper right corner, you see all these different colors. That's because different solutions of chlorides will form different colors. So you could actually identify what the element is based upon the color it forms. Another way you could do this is through what we call a flame test, which is what's going on in this bottom right corner. And all it is just a little bit of the salt put onto an inoculating loop that you would use to streak out bacteria, and you just stick it into a flame and we get different colors. And based upon that, we can identify what the element is. It's why people can look at fireworks and say, oh, I know what that is. We could also use an emission spectrum, which we did once upon a time ago. It's where I gave you guys those little glasses or the little grates to hold in front of your face. And I had the tube up in the front of the room, and I turned on the tube and it would glow. Then you look at it through the glasses and you'd see all those lines. That would be an emission spectrum. And you could actually use that to really identify, oh, wait, there's not just one element, there's like 2 or 3 in there. So we could actually identify elements just by burning them and then staring at it with a pair of glasses. There are other element or compositional analyses that are possible. I just wanted to tell you that they exist. They turn out to be insanely fancy. We don't do them in high school, namely because the equipment is too expensive. And we wouldn't necessarily have time to do one within the period, let alone actually make sense of the data. But what it could tell you is, if you were to look at this picture right here, and if I were to ask you, what is it? You would look and say, ground up rocks, volcanic rock, it's sand. I don't know what that is, but it turns out, if you did the chemical analysis, that's an illegal drug. And I'll leave it at that. But this is an actual illegal drug. But you couldn't know just by staring at it. But it turns out there are ways to test it to figure out what it is without needing to do something illegal. We could also look at liquids or things dissolved in liquids, and we could deal with solubility, so we could figure out, so for salts, like, well, really, is this what I think it is? So you could look at how soluble it is, or whether it's polar or non-polar. Does it dissolve in water and alcohol, or in oil, or where does it dissolve? Does it turn out to conduct electricity? Does it melt? If it melts, that tells you something about it. If it doesn't melt, that tells you something about it. There's lots of things that we can do. These are some tests that you actually did in physical science when you were freshmen. So there's lots of ways that we can start to distinguish between substances. One of the ones that we did in this class that you didn't really do as a freshman was a titration. Titrations are used to figure out concentrations, to figure out amounts. They don't tell you what it is. You have to figure that out separately. A titration will tell you how much of something there turns out to be. And it's basic technique. We've done this before. We did 3 labs in a row. You have something that you're trying to figure out. You put an indicator in here. Hopefully you're correct with your indicator, because if you have no clue what this is, you might have to do this several times using several different indicators. You have a burette that will have a liquid in there, you know what the liquid is. Standardization just means you know what it is, and you've tested it to make sure that you know what it is. You add liquid in, so you dump in until we get a color change or a faint color change. That then tells you something about the pH or the concentration of hydrogen ions, and if you know that, you could then figure out, doing some backwards math, the composition of whatever it was in here to begin with. So that's not so bad. The catch is they don't always use phenolphthalein. There's all sorts of other indicators, and you always want to pick your indicator to match where you think the equivalence point will be. If you think this is a strong acid that you're dealing with and you want to deal with a strong base, so we want to go and have our indicator be changing its color somewhere around 7. So if you were to look at this picture here, it tells you, well, here's just the pHs of normal things. So if I were dealing with like milk or something around here, if I wanted to figure out its concentration, normal range, this would be for, hey, I'd use phenolphthalein for things in here. If I were using battery acid, that might be a little hard. If I'm using lye, I wouldn't want to use phenolphthalein. I'd probably want to use something else. Or if I'm using like baking soda, that's going to change things a little bit. So it does matter what indicator you use. We're going to give you something that uses phenolphthalein. The last technique that you were taught was Beer's law, where you had absorption equals the extinction coefficient times the concentration of whatever you're looking at times the length the light moves through. Meaning when you have your cuvette, you have liquid in here. What you do is you shine a beam. We know how much light goes in, we know how much light goes out, which means we can figure out how much is trapped on the inside, how much is absorbed, and that absorption has to do with how long did this go through, because the more the light goes through, the more, or the longer the path the light has to travel through, the more light's going to get absorbed. We make L always 1 centimeter because it makes our life easier. Concentration is proportional to this. The extinction coefficient is just the slope of the graph. So what you could do is, if we have some way of making colors, we can test for their concentrations using spectroscopy. This does not work if you're dealing with clear liquids. It only will work if you deal with something that changes the color. If you're making it cloudier or red or blue or green or yellow, that's the only time you can use spectroscopy. So if you're given like a solid, spectroscopy might not work. But if you're given different liquids, spectroscopy might work, especially if they turn out to be colored. So your lab final is going to be next Friday, because we'll finish all the presentations Monday through Thursday. It'll be easy. So what you're going to be asked to do is figure out an unknown. You're going to be told the unknown on Monday. Or actually, sorry, I'm going to give you your unknown on Thursday after we finish the presentations. Your job will then be to figure out, what are you going to do to test it? It's going to involve either density, D equals M over V. It's going to involve a titration. It's going to involve Beer's law, meaning spectroscopy. Or you're going to have to do a list of, well, here are the compositions, and here's how this thing seems to look, or here's how it would change color in a flame test and things like that, and then figure out what it is that way. You are going to need to figure out your own procedure. You have had all year of dealing with this stuff. If you have been throwing away your labs, this might turn out to be bad for you, so hopefully you've kept some stuff. I will provide you the actual materials. You need to come in knowing what to do. You will have 1 day and 1 shot at this. If you are not here on Friday, that's going to mildly suck.